In the last session, I apologise for posting only half a video. It wasn't until somebody was puzzled and asked the question, did I miss something? That I looked at the video that I'd posted on YouTube and found that I'd only posted the second half of the video. So if you haven't watched the whole of the video about engraving with cast and extruded acrylic, then please go back and watch that. And I apologise again for wasting your time the first time round. Now today we're going to tackle another part of the acrylic working process, which is cutting. Now cutting cast acrylic is different to cutting extruded acrylic, but in the first instance we're not going to look at the differences between acrylic. We're just going to look at acrylic in general. You might think that cutting is a very simple process because, hey, acrylic's a very soft plastic material. Remember last time I said to you, it's a unique material in that it's like water. It boils and evaporates at 200 degrees C. That's how cutting takes place. It's not a chemical process like wood or cardboard or leather. It doesn't produce huge amounts of horrible smoke. So the process of cutting is not a chemical process. It's an evaporation process. And that causes all sorts of strange problems when it comes to cutting. For those of you with a diode laser, you might think this is relatively unimportant to you. Trust me, you can see things with a CO2 laser that you cannot see with a diode laser, because the diode laser has got properties that do not allow it to cut acrylic. This is a graph of what they call absorbance. That's the amount of energy or light energy that will be absorbed by material. We're only running from 800 to 2300, in other words 2 microns. Well, we go up here to 10 microns, and already at 2 microns, look, we've got nearly 100% absorbance, 95% absorbance of energy. That's why we can damage PMMA with 10.6 micron wavelength of light, 10,640 nanometers, whereas you guys with a diode laser are somewhere down here. That's where you are on the scale with your diode laser. So the pink here is absorbance, 0, and the red scale here is transmission, i.e. the amount of light that passes through the material. Well, you might say, well, look, it's 95%. So where's the 5% that I'm missing down here? Well, 5% is reflected. You're not going to be able to cut or even engrave clear acrylic with the diode laser. Coloured acrylic has got different properties because the dye in the acrylic is absorbing the energy. It's not the PMMA. We're all familiar with how lenses are portrayed and all the specifications associated with lenses that the manufacturers provide for us. One of the biggest things is the way in which this cone, if you like, of energy below the focal point increases more rapidly depending on the focal length of the lens. So I've got a 25.4, which is a 1-inch lens, which has got an even bigger cone than this 1.5. Let's go and just verify that for a minute, and then we'll start working on from there. Okay, now I've set this to the nominal focus for this lens. This is a 25.4. We've got a 25 millisecond pulse. I'm now going to move, and I'm going to drop the focus by 1 millimeter. And we'll do another pulse, 25 milliseconds long. 11, 12. So let's just go back and do that same test again. But this time we'll run the test, instead of at 25 milliseconds, we'll run it at 125 milliseconds. So we'll add 0.1 of a second to the burn time. That's an interesting observation, isn't it? Look, we've allowed more time, but we haven't got the same size dots. So what is going on beneath that focal point? What is the real size of that beam? Here I've got a piece of 10mm thick acrylic. Well, the nominal focal point on there said that it should be 7 or 8mm. So let's try 7mm. I'm going to run this at a speed of 5mm a second. And we've got full power, 70 watts, running on this machine. Cutting 10mm acrylic with a 1-inch lens. I mean, that's ludicrous. Now I'm going to turn some air assist on. And it didn't quite make it through. Let's set it back to where I thought the focal point should be, which is about there. And I run the same thing again. Two things I want you to look at. Number one, here's what my dot test said the focus should be. And it made it, what, 9mm through a piece of 10mm material. Here's what my line test at the correct speed told me the focus should be. And it just about made it through all of 10mm. The other interesting point that I'd like you to look at is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10mm. Has the groove grown from that to that as I've gone through a piece of 10mm material? The answer is no. Look, it's virtually a straight, parallel-sided cut. How can it produce a straight, parallel-sided cut when the evidence that you've seen with your eyes says that I'm not going to get a parallel cut? So something weird is going on when we talk about cutting. Now, I'm not going to go into the theory of how lenses actually cut, because I've dealt with that at length on my series elsewhere. It's a very interesting subject which I spent 4 years of my life trying to track down exactly how this phenomenon happens, when all the evidence says it shouldn't. Look, it has actually just fallen off. It was hanging on there by a thread. But look at the cut. That doesn't look like a proper cut, does it? Even though the piece of material fell off. That was a 99.9% cut. But what on earth are all those marks there? Let's go and have a little bit of a closer look at that, shall we? Okay, now you thought I was mad trying 10mm thick. Well, we're now going to go for 20mm thick acrylic, but I've reduced the speed from 5 to 1mm a second. Do this again because there's something else that I want to show you. Now, I'm going to stop there. There's a very interesting point to be made just here. You can see the way that that beam is bending towards the left at the bottom. Well, people argue that that's because of reflected light. The light is going downwards and bouncing off the surface and travelling round at the corner. Now, my point is very simple. If the light is doing as people claim and it's reflecting round that surface, then when I start the beam up again and I'd have no motion, that beam, that shape is going to remain the same because the light is going to travel around and get reflected off that surface. Let's watch what happens when I press the pulse button again and turn the beam on without any motion at all. So it didn't travel around the curve. But the other thing you'll notice is it's sort of gone frosty, and then it cleared up once I started the motion again. Let's take a look at the beam shape, because remember, is this going to be tapered because it's 20mm deep now and I've only got a 1-inch lens in there? I mean, on that basis it should be probably something like 5mm wide at the bottom of that cut. Just so there's no confusion, I've put a black mark on the flat surfaces either side of the cut. So now you can see what the cut is. Does that make sense at all? Who would ever consider cutting 20mm thick acrylic
with a 1-inch focal length lens. It's just not possible. You've seen it for yourself. It's not possible unless you understand how cutting actually works. So this is the first and biggest myth that we're going to dismiss in this session. Everybody tells you that you need lots of power and a very, very long focal length lens to cut thick materials. I've got 70 watts and a 1-inch lens, and I've cut through 20mm thick acrylic. You might say, yeah, but it hasn't fallen off. Look, I'm going to do just this with my fingernail. And the only thing that was holding that on was that little teeny weeny piece just there. Now, let me try and explain that with one of my dodgy diagrams. There's our material, 20mm thick, and there's the edge, the last edge. Remember, the beam started off over here, like this, and then it gradually started doing things like this. And by the time it got to here, it was doing silly things like this. Right, it's coming down and then it was curving off at the bottom, like this. Okay, remember, light travels in straight lines. So it gets to here, and now the light travels straight the way down. And it leaves this piece here. Up to a certain point, that is the cut that's caused by the actual laser beam itself. And beyond that cut, what you've got is heat-induced cutting. This is not a chemical reaction, this is a vaporization process. And hot gas that's created during this cutting process travels downwards and causes this strange curved cutting action. Now, the faster I travel, and we can prove this, we can do exactly the same thing again, and I'll show you some very interesting phenomena. What will happen is the beam will come down and it will travel further and further backwards, but it will travel so far backwards that it can't actually get through to the bottom of the cut. And so what you get is a rather weird, intermittent, jagged cut at the bottom, a heat-induced chaos. Okay, so I've now pushed the speed up to 3mm a second, and now you should see this heat-induced chaos at the bottom of the cut. See the way the bottom of the cut is waving around? When we were cutting the 10mm material, you'll remember those strange marks along the bottom of the cut, where I said it was only just cutting through. Well, that was heat cutting. That wasn't laser beam cutting. The point is, if you get beam drag, which is what some people call it, the drag is caused because the laser beam is going too fast and you have to slow down. Basically, you're always looking for a beam to sit upright for the whole depth of your cut. Okay, now look, this 20mm acrylic, I will just point out to you that I got this as scrap from a large local plastic distributor who has got 150 watt and a 200 watt CO2 laser. Do they cut this on their machine? No. This has been CNC routed, because look, all these rags on the bottom tell you this has come off a CNC machine, and the surface finish tells you it comes off a CNC machine. So even they don't cut 20mm acrylic with their 200 watt machine. So I'm going to show you now what I just spoke about. If you go slow enough, you can get a good cut. Okay, now I can't do this manually with the pulse button and the speed, because the speed only allows me to go down to 1mm a second. So I've had to program a line so I can get down to 0.5 of a millimetre per second. And I'm using the same power as I did before, full power, 70 watts. And I've got my focus set to 6mm. Now this is obviously a piece of cast acrylic, 20mm thick, and it's supposed to be difficult to get a flame polished finish on a cast acrylic. Now you will see how this flame polished finish can be achieved. If we can hold the liquid phase long enough, in other words we keep the heat in the cut above 160 degrees C, the liquid will actually flow on the kerf walls, and it will disguise all the little cuts and marks that are on there, because liquid flows to a lovely, perfectly smooth finish. Now you'll note the cut is nearly upright. We've still got some heat cutting at the bottom, but it's hardly there at all. But you can see it actually is out of control from about halfway down. So the cut is now finished, but I'm now very carefully going to tease that cut apart. Okay, now look what's happening. Can you see how sort of flexible it is? And can you see at the bottom there, look how this is very soft, this material now. And just down here, where the cut started, it's now hardening off. Now we don't have a huge airflow there at the moment, but what I'm going to do, I'm going to turn my airflow on full. I've only got one of these little silly little pumps of 3 psi, but listen to the airflow. We're now going to run the same test with air assist, because previously I had little or no air on. I wasn't attempting to cool the cut down. The cut was generating its own heat, and this beautiful surface that I've got on here was caused by the liquefied surface staying liquid and levelling out. So what happens when I put air assist on it? And here we go. We seem to be getting a slightly cloudier finish if you look. We're getting less turbulence at the bottom of the cut. So if we catch that in a different light, you can see that it is a lovely sort of a lovely smooth polished finish. Virtually no marks on it at all, but hang on, what's that? Why is it rough along the top there? Acrylic supposedly melts at 160 degrees C and vaporizes at 200 degrees C. This is information that I gained from the big wide world web. How true is it? I'm going to see if I can use my thermocouple here to measure what's going on a millimetre or so away from the cut to see if I can get anywhere near those temperatures and verify roughly what's going on. And we should just begin to start seeing some temperature rise, I would think, about now. Well, it's melted itself out. Well, we're going to try and see if we can measure this surface temperature here roughly as the cut moves along. How accurate this will be, I've got no idea. But all I can tell you is that I've tried measuring it with this, but it doesn't give me anything like the sort of correct information. So behind the cut, look, we're sitting there at about 160 degrees C. So that's not far off what is claimed. 170, 180. So that's the temperature of the hot gases that are going in at 200. Wow. So that's why we're getting the liquid phase. Let's take a quick look at the shape of the cut as I run into the surface. Now we'll do the same thing with full air assist. This suppression of ballooning here as caused by the air assist, whereas here we're getting more damage higher up to produce this ballooning effect. Now, I'm not even going to begin to explain why and how that ballooning effect happens. This is not caused by the beam expanding below the focal point, because if it did, why didn't it carry on right to the bottom? Why has it stopped somewhere towards the bottom here? That's something, as I mentioned earlier, you can go back and check out how cutting actually takes place. We can clearly see that we've got some Perspex XT here, extruded, and this we're fairly confident, because it's so thick, is cast acrylic. I've taken the lens tube out of here. So what we're going to do, we're going to bounce the raw laser beam down onto this material and then onto this material. Now, the fact that it's a raw laser beam means there's no focal distance here, so it doesn't matter about the height difference between these two materials. We're going to see if we can produce different thicknesses or widths of damage on these two materials, which would indicate that they've got different damage thresholds, or are they both the same width of line. So we're going to run this at 10 millimeters a second, full power, 70 watts. Now, first of all, let's try and catch that in the light. Can you see how shiny that is? That cut? That is what we would expect of extruded acrylic. Let's compare that to this one. You see, that's not shiny at all. That's just matte. You'll see that the extruded has produced a wider cut. So that means its damage threshold is lower. The other thing that you can see is there looks to be sort of a ridge around the outside of the extruded acrylic, and yet the cast acrylic is a nice clean edge to it. I mean, you can hear it. There's an edge to that cut. Even though this is not a focus cut, there's still an edge to that damage there. Not the slightest hint of a burr at all. Okay, so there's a very quick, simple way of telling whether or not you've got cast or extruded acrylic. Just take your lens out and burn a little groove. Now, the reason I'm showing you that test is because there is a myth that's been going around for a long time that you can quickly tell cast acrylic from extruded acrylic because a cut edge will produce cracks when you put alcohol on it. Let's see whether the myth is true, should we? Some in there, some in there. And let's wait for the cracks. How long do we have to wait? Well, the myth doesn't say. And to be honest, what I can tell you is that after a few months, I have seen cracking on some of my glued joints. I don't glue with this stuff. So we've already tested that with alcohol, and there's no signs of cracking there. We've tested this with alcohol, and there's no signs of cracking there. So let's go a little bit more aggressive, should we? And this time we're going to use my acrylic cement. I mean, look, I've put loads of it on there. If it's going to do any damage, it should certainly be doing it fairly quickly. Oh, look. Catch it in the light, right? Look, there are some cracks in there, but it's not with alcohol. That's because I've used my acrylic cement on it. Well, I can't see any signs of cracking on there. So I think we've dismissed another myth. The alcohol myth doesn't work, but the acrylic cement may work. It's not always as quick and easy as that with extruded acrylic, because I use a lot of extruded acrylic and it's very rare for me to see cracking on my joints. But hey, on this occasion we were lucky. So we can cast away the alcohol test as a myth. We can put the acrylic cement test in as a maybe. But the one thing that we can't change, and we get an instant answer for, is running the laser beam across the two materials. One is shiny and the other's dull. Right, now for this next test I've got two pieces of acrylic here that are roughly the same thickness, 5mm, that I'm going to use for cutting tests. But I don't know whether they're both cast, whether they're both extruded or what. So let's carry out my quick burn test on them. And see what we've got. Well, much to my surprise, these are no-name products and they're both look like they're cast. That is a surprise to me. Let's try another two. Both look cast. Okay, now this is a bit thicker, 6mm, but I'm fairly confident that this is extruded acrylic. No doubt about that. That is clear and shiny. So look, there is absolutely no doubt about that. This is matte and this is virtually clear. We've got a piece of cast and a piece of extruded. They're not quite the same thickness. One is 5 and the other's 6. I'll see whether I can find a piece of 6mm match. It says it's Perspex, but Perspex do both cast and extruded acrylic. There's nothing on this that says it's extruded, and there's nothing on it that says that it's cast. Generally, extruded is clearly marked and cast isn't. So we'll just have a quick look. And just from that little test there, we can see that that's matte, therefore this is cast. So there's no way we're going to get these two pieces of material muddled up. Now this may be a very short focal length in here, and I've got a very short nozzle, but it's still a cutting nozzle because it's got a very small orifice in the end. You've seen how it performs on thick material. Let's see how it performs on thinnish material. But we do know that the nominal setting for this nozzle is 6mm. Well, it was for very slow speeds anyway. It may change if we put the speed up a little bit, but we're not going to go up that fast for 6mm material. We're only going to go up to probably about 6 or maybe 8mm a second. Well, 8mm a second just about made it through. I'm now going to turn my air assist out to virtually nothing. So just enough positive pressure on there to protect the lens. We'll use the same settings that we've just done. Lots of chaos cutting on the bottom edge. So if I can catch the light on there just right for you, you'll see that we've managed to get rid of most of the chaos marks purely because I've removed the air assist and it's no longer trying to cool the cut. Okay, so we're using all the heat generated by the laser beam to get almost through the material in a fairly smooth manner, but it's still got those striations on the surface there. We'll go to the XT and see what cut that has. As you can see, we've got a few marks along the bottom here, but very few. So we've got this wonderful effect of the heat being retained in the cut for some reason or other, which is allowing us to get a very nice, shiny cut. Now, if I slow that down a little bit more, I dare say we should be able to get a nearly perfect edge cut. Catch it in the light right, and there are just a hint of some marks on there. But basically, that's a flame polished edge. So we'll now turn full air assist back on. The cut is now vertical. And again, it's difficult to see it, but there are just a few striations on there. Okay, particularly along that top edge there. You see that? So the air assist is having an effect on the top edge, but once it gets into the cut, it's still a pretty smooth burnished cut. It's very, very shiny. The point being that with extruded acrylic, the heat is retained in this cut a lot better, and it flows along the surface of the material and produces a burnished edge very easily, regardless of whether you've got air assist on or not. So you get a much better edge with extruded acrylic than you do with cast acrylic. With cast acrylic, if you want a shiny edge on it, you've got to run very slowly so that you can get heat into the cut and retain heat into the cut. Now remember, I told you that I get a lot of my material from a local large plastic distributor who's got some big industrial laser machines, 200 watts and 150 watts. They're big bed machines, but I suspect this is cast acrylic because it has not got a shiny edge. But look at all these striations along the edge here. He's got the same striations that I've got, even though we don't have the same machines. How can that be possible? The point I'm really making there, it looks as though this is not a machine problem, this is a material property issue. And I know what that material property issue is because, as I said, I've had absolutely perfectly smooth motion and still managed to achieve these marks. You've already seen that this material has got weird cutting properties. It tends to vaporise after it's boiled, but the beam itself is not like a drill. So the beam itself that we're firing at this, this is even after it's been through the lens. So this is what's happening at the material surface. So this diameter here is probably only something like about 0.2 diameter. Okay, but even within that 0.2 diameter, you've got this strange intensity profile, which means that we've got very high cutting possibilities at the center of the beam. And as we move away from the beam, the cutting possibilities get less and less and less and less, to zero almost at the edge of the cut. When we cut our thin material, you'll notice that the beam, I'm not going to put the ballooning on it, but the beam was shaped like that. Whereas when we were cutting the 20mm thick material, that same lens was cutting like this. It was cutting a much wider beam. And that's because we were running faster at 5 and 8mm a second, so the beam didn't get a chance to penetrate as much. And it didn't get a chance to penetrate as much because penetration is a function of intensity. The greater the intensity, the faster the damage. So this pointy bit here shows that we've got lots of intensity at the center of the beam, and as we get towards a little bit further out from the center of the beam, the intensity is starting to drop off, and so we do slightly less damage. With this very slow speed, what was happening is, because it was acting very slowly, we were actually probably cutting right out here somewhere. We had a much wider cut because this central part of the beam had a chance to get much deeper, but this outer part of the beam was actually cutting a much wider curve. Now I hope you can understand that bit. But there comes a point where this has not got enough power for the speed to do cutting. If you go back and look at the edge of the cuts where the cut started and finished, you'll see that there's bubbles on the surface where you've got the boiling action rather than the evaporation action. Okay, and when we see that cut that I asked you the question, when we looked at the cut like that, if you remember, and it was a cut that looked like that, and it had all this rubbish on the top here, so that was what our cut looked like, okay, with all its striations across it like that. Okay, if you look carefully, you'll see that this here was actually probably something like that bit there, okay, and there were lots of bubbles on it because the air assist was coming in and freezing those bubbles in the surface around that part there. So go back and take a look at the video and you'll see that roughness there that's caused by the low intensity part of the outer part of the diameter of the beam. Whereas the central part was busy doing this, and then it ran out of puff and it started doing this at the bottom. Okay, the chaos. Because there just wasn't enough power here to get further than that in the time that we gave it, the speed that we were running at. Give it more time, and as you saw, we were able to get right the way through. So there's a strange property associated with this beam and this material. The first part of the beam will pierce in quite quickly and produce a cut that looks like this. Okay, but as that is doing that, around the outside of that cut, what we have is like this part of the beam is busy producing some vapour around the outside. So we've got a cut with some vapour around the outside like that. Now the problem is vapour is material that doesn't cut. Okay, it absorbs energy, but it doesn't actually cut because it's vapor. There's nothing there. So effectively what we've got a hole which the beam is making, and round the outside of the hole that we've just made, we've got a little vapor pack like that. So the beam is now travelling forward to a new position, and it can't cut this until it gets to here. And when it gets to there, it hits new fresh material, solid material, not vapor. So this cutting action is basically one of cut, pass over the vapor, cut, pass it, and of course then what happens is as soon as you do this, you get a new little vapor screen around the outside of that, so it jumps over that and then it starts cutting again. All right, and then you get a vapor screen, and then you cut again. So effectively what we've got here is a built-in mechanism for intermittent cutting. And when we look at the way that these cuts overlap, you'll find that this is the cause of those striations. Cut, intermittent cut, cut, intermittent cut. The surface is very slightly like this on both sides of the cut. I exaggerate slightly, but that's the cause of these cuts. It's nothing to do with the mechanics of the machine, it's all to do with the intermittent cutting process which this material exhibits. It's a unique material in many different ways. This is just one of those ways, and the only way that you can get rid of this surface damage is to put enough heat in there so that the material tends to flow and it becomes flattish, and then you get your burnished finish. So I hope that's another myth that bites the dust and saves you hours in trying to find a mechanical problem to solve to fix your striations in acrylic. It ain't going to happen. So as I said, acrylic is a very difficult material to cut, even though it's a soft plastic. It absorbs energy, and that energy is going into a phase change for the material, not a chemical change. Chemical changes tend to produce an exothermic reaction which aids the cutting process. When you change from liquid to steam, it requires a huge amount of energy to cause that phase change. And so this material cuts at about half the speed of wood or leather, where you've got a chemical reaction taking place. So the golden rule is look at the shape of the cut that you get. If it's bending backwards, you're going too fast. You can't rush acrylic. It is its own master. Depending on the thickness that you're cutting, you will be able to change the lens to make a slightly more efficient cut. As we've seen, there's virtually no difference in the cutting speed of these materials. The thing that changes is the edge finish. You can throw air assist as much as you like at extruded acrylic and it doesn't have an effect on the edge finish. Throw air assist at cast acrylic and it has serious consequences. So cast acrylic, you need to back off your air assist if you want a clean edge. It won't change the cutting speed, it will actually slow the cutting speed down. But hey, don't take my word for it, try it for yourself. I've been using a very short focus lens here and I'm cutting 6mm material with it. I cut 20mm material with it as well, but hey, it's not something you would normally use for 6mm material. You'd normally be using probably a 2-inch lens. But I'm going to stay with this lens, and at the moment you can see that this is just an ordinary Chinese PVD lens, a cheap lens. This is the one that cut through that 20mm thick acrylic. Now I'm going to do this to the lens. Now you'll notice something about what I've just done. It was flat side up. Flat side up? Hey, that's the wrong way for a lens. Are you sure? Well, we'll put the lens the right way round now. Don't worry about the way that I'm holding that lens in there. The lens is completely stable. It's not rattling. It was cutting best at 7mm. So let's put it back to 7mm and just do a quick test with our XT material. Now, with or without air assist shouldn't make any difference because this is XT material. So let's put it back to 5mm a second. And now we've got significant beam drag at the bottom. significant beam drag at the bottom, and it didn't come out. Let's go down to 3mm a second. Now we've got a nice vertical cut. And we've got the air blowing right through the cut because we're producing smoke everywhere. That is not a good cut at all. It's got quite a lot of burnishing on it, but look at the marks on it. It's not doing a very good job of flowing the material. This is with air assist on, and the lens the right way. Just remember, we've just lost 40% of our cutting speed because I've turned the lens the right way round, and we've got this crud across the top that we didn't have before. Okay, let's turn the air assist down to virtually nothing. Just a whisper. Remove the air assist and we've virtually got rid of that set of striations across the top there. This is now a smoother cut because there's less cooling in that cut. We've allowed the heat to build up and we've got a much smoother cut. And that really takes us to the final myth in this session. Is there a right and a wrong way for a lens? I'll leave you to make your own mind up and experiment for yourself.